Hello, my name is Usman Sheikh, and this is the presentation for the paper ID 27 for ICCIML 2021. The title of the paper is Detection of Mobile Phone Usage While Driving Using Computer Vision and Deep Learning. This work was completed by Yeoh Hwei, Usman Sheikh, and Nurul Ezaila Alias. Let's look at the motivation for this work. On average, an American spends approximately 5 hours per day on their mobile phones, and this can contribute to distracted driving if you use your mobile phone while driving, and this is actually a critical topic in traffic safety. So driver distraction is defined as the deviation of a driver's concentration from their driving task. So in countries such as Malaysia, Singapore, and Australia, approximately 1 to 11% of the drivers still use their mobile phones while driving. Okay, so the in order to catch drivers that actually are distracted while driving and using their mobile phones, many police traffic officers needs to be deployed at checkpoints at different locations in order to monitor these behavior. Okay, a camera-based automatic image recognition would be really helpful in order to detect such a traffic violation. So in order for us to train a machine learning or a computer vision system to detect what we call drivers are distracted from driving using their mobile phones, we would require a lot of training data set. Okay, however, in our case, the training data set for drivers using their mobile phones is fairly limited. Okay, so recent researchers have implemented different image recognition system to detect for the usage of mobile phone while driving, but the accuracy and computation time for these systems varies with the complexity of the problem. And at the same time, the majority of the prior work is based on the in-car camera system. That is, the camera is actually mounted inside the car and the imagery is actually captured from such a scenario. Okay, this may be suitable for driver assistance systems. However, the scope of our work is to actually have a system that can be installed beside the road and is able to monitor the driver from this traffic. Okay, so the objective of this work is actually to design and develop a convolutional neural network based approach for a camera based automated image recognition system that is to detect the driver using mobile phones while driving. And of course, the second objective is to provide a performance evaluation between prior works and also the proposed work. The scope of our work is actually that the camera is actually set on an overhead bridge, capturing the driver's driving condition from a front view during daylight, and the data set, which includes a lot of reflection on the windscreen, is actually removed. And we are trying to detect a single object in car image, okay, that is the driver using their mobile phone, and we are not actually considering other distractions. We also assume that the bending of the driver's hand towards their head is considered as an action of holding mobile phone, as detecting the mobile phone itself from a far distance is fairly difficult. Let's look at some of these related works. I have actually placed here a couple of related works in this slide. The first one is driver cell phone usage detection using near infrared images, and this is actually based on a camera that's placed overhead a gantry, and you can detect the windshield as well as the face. The second work is actually based on a camera placed inside the vehicle. The third work by Sheikh in 2015 is also based on a camera placed inside the vehicle, and this final work, okay, that is the multiple scale faster RCNN, is actually also placed inside the vehicle, which is actually not the kind of a scenario that we are looking for. Now there are some works that are actually based on placing the camera outside the car, that is on a roadside gantry. So for example, a work from El Katan 2019, Alkan 2019, okay, and also Ulhaq 2017. These are some of the works that actually based on a camera that's actually placed outside the vehicle at a roadside gantry. Okay. Now, what kind of methodology that we employ in our work is basically we start with setting up some software tools, and then we perform some image acquisition, we perform some data processing, training the data, and then we train the configuration, and then we test our proposed framework on our testing data set. We perform some system evaluation, and then we produce the results and compare with the existing works. This is the kind of the view that we have for our data collection. As you can see, the camera is placed on a overhead bridge where we can see directly into the cars as well as the windscreen, and if the weather is permissible, we can also see the driver itself, and then also what is the behavior of the driver and the conduct of the driver. The software tools that we use is actually TensorFlow libraries in an Anaconda environment, and we have collected 2340 images, and then and 1340 images are actually left, okay, after we discard some of the unclear images, and then the images are saved as JPEG with a 4896 by 3264 pixel resolution. The first step of data pre-processing is actually we want to actually detect a single person, okay. So we reduce the resolution of the image to 900 by 1000. With the objects that we include are cars, we don't include motorcycles. The two data set that we have is not call and also call. We also flip the images to increase the number of data set that we have, okay, and all this annotation is done manually and is saved as an XML file. Okay, so you can see here several images showing not call, that is, the driver is not doing any call, and then we have a left-handed driver image followed by a left-handed driver image performing a call, and also a right-handed driver image performing a call. What we use is actually a faster RCNN with the Inception version 2, where 63% of the data set is used for training and the remaining 37% is used for testing. We train for 20,000 steps with a batch size of 1, and the training is done up to 14 times on our 4th generation Intel laptop, which took about 64 hours. Our learning rate is 0.0002, and the process is terminated when the loss is less than 0.07. Alright. And looking at it, we have this future network which receives the resized input images of 600 by 1024 pixels, and this is actually sent to the convolutional model to generate the feature maps. We use a region proposal network, okay, and then we also have a detection network which is called the second stage box classifier. The following is actually the results. We can see that the objectness loss in our training as we go through the training process actually reduces. We also have the localization loss in our training also decreases as we train. And this is our box classifier classification loss per period of training, and also the box classifier localization loss in the training stage. And the total loss in the training stage is now actually very low at only 0.2. Okay, once we applied that trained what we call network, and we applied on our test data set, we can see that it actually successfully detects the driver which is performing call or not call. So on the left hand side we have two images flipped to generate two different sets of images whereby the driver is not performing any call, while the right hand side you can see two images of driving actually is distracted using a telephone while driving, and all these four images are successfully detected by the trained neural network. In this image, in this optical experiment, what we are trying to do is whereby the face of the driver is actually partially cropped due to some film or some blocking where we can't see the complete face of the driver. And in these four images, it is demonstrated that our proposed RCNN can still classify correctly whether the driver is actually performing a call or not performing a call. Alright, and what about this one? This one is actually showing that the hand of the driver is up to the shoulder of the driver. Okay, so in this case, again, once the hand is up there towards the head, the classifier actually detects the call. And in this one, you can see that in these sample images, we also have what we call a passenger together with the driver, and we can still detect whether a call is being made or not by the driver. Sometimes the classifier also performs incorrectly. So in this one we can see that it is actually both of the passenger and also the driver is not performing any call on the left hand side, but it's still predicted as call, while on the right side what we can see is that the driver is actually just putting his hand on the window, but because our training is anything that any image where the hand is towards the head is considered as what we call call. So we use a couple of valuation outcomes. We use average precision, we use mean average precision, okay, and we also use mean average recall. Okay, so this is pretty standard evaluation metrics applied by the COCO. Okay, and of course we only consider large detection area, and this is the result for MAP with IOU of threshold of 0.5 and threshold of 0.75, while this image actually shows the MAP with IOU threshold of 0.5 to 0.95. Alright, we also have a recall, an average recall, and mean average recall. Alright, and these are the results for mean average recall with 1 detections per image and mean average recall with 10 detections per image. And from our evaluation we obtain an accuracy of 88.71%. And when you compare to other existing works, we found out that the existing works are mostly based on in-car images, while our work is one of the very few works that actually based on images taken from outside the vehicle. So the conclusion is that based on our 1348 images, we develop a convolution neural network which is the faster RCNN, and we obtain a detection accuracy of 0.8871 or 88.71% to detect whether a driver is performing a call or not performing a call. Alright, so for future recommendations, we can also increase the data set to be more balanced, and we can also include other kinds of what we call violations such as texting, and we can also improve the model by automating the data pre-processing. And since the training takes a lot of time, we can actually increase what we call the training accuracy by increasing the step, okay, using a more powerful GPU. And we can also try to compare with other pre-trained CNN models such as Inception version 3, ResNet, or MobileNet. Thank you very much.